with our favorite rocket ship, jumping through the sky, little lights fly on. Alright, so I'm Thomas Gardner, and today we're going to talk about special relativity. Alright, so consider this hypothetical. Alright, so you're on the ground, like that, and you shine a flashlight. Well, if you could observe the speed of the light coming from the flashlight, it would be this 3 times 10 to the 8th meters per second. But what would happen if you were on a train moving at speed v and another person was in front of you viewing that flashlight? How would he observe it? Well, according to Galilean relativity, the speed would be c plus your velocity, which wouldn't make sense because no velocity can exceed the speed of light. So, in actuality, Galilean relativity breaks down as you get closer and closer to the speed of light. Alright, so now that we know that the speed of light is the same for any reference frame, people decided to test if this was really true. And these two guys named Michelson and Morley decided to test the speed of light in 3 different reference frames. The speed of light with the velocity going the opposite way, the speed of light, and the speed of light going in the same direction as the velocity. And what they found out was that for all 3 tests, c equaled roughly 3 times 10 to the 8th meters per second. They were all the same. And so they concluded that despite the reference frame or the velocity, the speed of light is constant. And so a young patent clerk by the name of Einstein took those ideas and came up with the theory of special relativity. And that theory has 2 postulates. First of all, that the laws of physics are the same for all inertial frames. And an inertial frame is any reference frame and that has a certain constant velocity. Second is the one that was figured out over there by Michelson and Morley, is that the speed of light is the same for all inertial reference frames. So the speed of light on a spaceship is the same as the speed of light, in your armchair. Another important thing to realize about the theory of relativity is that there is no preferred reference frame. Whether you're on a spaceship traveling at high speeds or back at Earth, there is no preferred reference frame. There is no backup or uniform or universal one. It's kind of actually narcissistic to think that our frame of reference on Earth, that while we're spinning rapidly and hurtling around the sun, while our entire solar system is spinning within the galaxy, and the galaxy is rotating in the universe and moving throughout the universe, that our sense of motion would be the universal frame of reference. Same goes for a spaceship. So basically, like we saw with our guy tossing the ball up on the train, what we observe is completely relative on where we are and how fast we're moving. Okay, so now we're going to get into some very interesting stuff, like time dilation. So consider this northeast graph right here, like on a compass. Say that you're moving just due east along here like that. Then, like that. you would move this far east and nowhere north. But say that you use some of that movement for moving north. You move the same distance, but you move less distance east than you originally would have. The same concept applies for space and time in a graph that they like to call space-time. So let's put space up here and time over here and consider the same principles. If you were not moving at all, then your time would just be like this, like you were moving east in the other graph. But say that you started moving at a constant velocity. Whatever space you covered would actually decrease the amount of time that you spent. And while this isn't very noticeable, it's not noticeable at all really in everyday circumstances, when you get closer and closer to this speed of light, some weird stuff starts happening. Alright, so now we're going to talk about how time dilation works. So we've got this one experiment right here where a person is shining a beam of light up to the ceiling where the light contacts a mirror and goes back down to the person. And it travels a distance of d up and then d back down. And this whole frame of reference is moving with a speed of v. So we've got the time that the person records for the beam of light to move up and back down as 2d, which is the total distance traveled, divided by c, which is the speed of light. Time equals delta x over velocity. So then we're going to have the same experiment going, but with an observer watching this frame of reference as it goes by. So this observer is going to observe the person shooting the ray of light upward and then observe it hitting the mirror and coming back down. But since this also has a velocity in the x direction, this person will observe the light moving both up and to the right, and so it will form this kind of triangle, hit right here and then go back down. And so this person is recording the time that the light takes in here, and this person is recording that time that takes the light to go this far. So we've got the delta t sub p over here, which stands for, the p stands for proper, and then we've got this triangle over here where the light travels d in the distance in the y direction, the horizontal velocity times the total time that it takes to go up and back down divided by 2. We're just trying to find the velocity that it goes up. And then in the hypotenuse direction is the actual path that the light travels, which is the speed of light times half of the total time, c delta t over 2. And so, because this is a triangle, we can just use our Pythagorean formula, which is this value squared plus this value, d squared, equals the path of the speed of light squared. And basically there's some simplification and moving around, but as you can see, when you solve for delta t, you get this 2d over c divided by the square root of 1 minus the horizontal velocity squared over the speed of light squared. And so the 2d over c equals the delta t sub p. And we're going to say that this 1 over the square root of 1 minus the v squared over c squared is going to be called gamma. And so we have delta t equals this t sub p times this gamma value right here. And due to the fact that this v value can never be greater than the speed of light, this gamma will always be positive, and it will always be greater than 1. So since this will be greater than 1, the delta t observed by the person outside of the frame of reference will actually be greater than the delta t sub p observed inside the frame of reference. And you can kind of see that because they're traveling at the same speed, but this person, or according to this person, the light travels this much farther than it does according to this person, which is an interesting phenomenon. But if there's an extra amount of distance with the same speed, the time for this one is going to be greater than the time for that one. And that's basically how time dilation works. One of the most practical applications of special relativity is the use of GPS. As of right now, there are 24 GPS satellites orbiting high above the Earth at a speed of 14,000 kilometers per hour. And they are accurate enough to measure one's location within 5 to 10 meters, which is pretty good. So how do they do this? Well, because of special relativity, it makes it even harder. So they're moving at a pretty high speed, far away from Earth. So according to special relativity and this mess up here, they're actually going to, the clocks are on these satellites are going to tick a little bit faster than the clocks on Earth. And while technically, looking at the equation above, special relativity would have the clocks tick slower on the GPS than they would on Earth. General relativity, which has to do with the gravitational field of Earth on the surface versus where the GPS satellites are, actually makes the clocks tick slower. And I think that's about 38 microseconds per day, which doesn't sound like a lot, but by the end of the day, it could throw off the GPS system by so much that a person in Columbus, Ohio could be recorded as by their GPS and see that they're in Detroit, Michigan, which for the GPS systems is completely off. So the GPS systems, some of them have a special clock that ticks a little bit slower, but most of them have the computers that perform the special relativity calculations and adjust the time accordingly. Thanks for watching, guys. That's the end of this video. For more information on other types of relativity, special relativity that I didn't get to, such as the twin paradox and length contraction, please see these links at the end of the video.
Climb aboard, get ready to explore, there's so much to find.